What if tonight you looked up and the moon wasn't the moon anymore? No warning, no countdown, just different. A new light hanging in the sky, roughly the same size, roughly the same distance, but not the pale, familiar, cratered face that's watched over every sunset in human history. Something else. Something that used to belong to a different star, a different system, a different corner of the galaxy entirely. We've done this experiment before. We've dragged distant exoplanets into our solar system and dropped them into empty orbits, watched them boil, freeze, or quietly wreck everything around them. TRAPPIST-1, when cooked in Mercury's orbit, Kepler 442b turned into a super-Venus a stone's throw from Earth. A frozen super-Earth from 21,000 light-years away nearly took out the asteroid belt. But every single one of those experiments kept a safe distance. We were rearranging the neighborhood, not touching the house itself. Today, we're touching the house. Because there's one object in our solar system we've never dared to swap out. And it's not a planet at all. It's the moon. And here's the part that should worry you before we even start. The moon isn't just a rock. It's a stabilizer, an anchor, a 4.5 billion-year-old accident of gravity that just happens to be exactly massive enough and exactly far enough away to keep this entire planet livable. Take it out, and you're not redecorating the night sky. You're pulling a support beam out of a building and hoping the rest holds. So what happens if we don't just remove it? What happens if we replace it, one alien world at a time, and watch what each one does to us? Before we drop the first candidate into orbit, you need to understand exactly what's actually at stake, because most people vastly underestimate what the moon does for a living. Around 4.5 billion years ago, in the chaotic infancy of our solar system, a Mars-sized protoplanet slammed into the young Earth in what scientists call the giant impact hypothesis. The debris from that collision, molten rock and vaporized crust flung into orbit, eventually cooled and clumped together into the moon we know today. It wasn't captured. It wasn't a passing visitor we happened to grab with our gravity. It was born from us, forged out of the same violence that shaped this planet, and that shared origin is exactly why its mass and its distance line up so perfectly. That perfect alignment is the only reason Earth's axial tilt has stayed locked at roughly 23.5 degrees for hundreds of millions of years, instead of chaotically drifting the way Mars's tilt is believed to swing by tens of degrees over geological time without a large moon to hold it steady. A wildly shifting axial tilt doesn't just mean unusual weather. It means ice ages arriving in centuries instead of millennia, entire hemispheres flipping between deep freeze and blistering heat on timescales too short for ecosystems, let alone civilizations, to adapt. Every stable season you've ever lived through exists because something the size and mass of our moon has been quietly holding this planet steady the entire time. So every candidate we're about to test isn't just competing on looks. It's competing against 4.5 billion years of near-perfect gravitational engineering. And so far, in every experiment we've ever run on this channel, nothing dragged in from another star system has come close to matching what evolved here by pure cosmic accident. Let's start with something that, on paper, sounds almost gentle. Kepler 10b sits about 560 light-years away, orbiting so close to its star that a full year there lasts less than a single Earth day. It's rocky, roughly 1.4 times the size of Earth, and it holds one of the grimmest titles in exoplanet science, the first confirmed rocky. World ever discovered outside our solar system, and one of the most hostile. Daytime temperatures there climb past 2,500 degrees Celsius. Hot enough to keep the entire sunward hemisphere as an open, glowing ocean of molten rock that never cools, never crusts over, never stops moving. Astronomers don't describe it as a planet with volcanoes. They describe the whole day side as a lava world. Now put that where the moon used to be. Pulled away from its scorching parent star and dropped into orbit around Earth at 384,000 kilometers, Kepler 10b would finally start to cool. Slowly. Over centuries, that molten crust would begin to harden the way a wound scars over, dark obsidian slowly swallowing the glow. For a while it might even look almost peaceful up there, a dim, smoldering ember slowly dying in our sky. But don't relax yet, because something else is already happening, and it has nothing to do with temperature. Gravity. Kepler 10b is denser and heavier than our moon by a significant margin, and mass, this close to Earth, doesn't sit there quietly. It pulls. Our tides, the ones rising and falling twice a day along every coastline on the planet, exist because the moon's gravity tugs at Earth's oceans. Swap the moon for something meaningfully more massive, and those gentle tides stop being gentle. Coastal cities built around a predictable 2-meter tidal range would suddenly be facing surges most of us have only ever seen in hurricane footage. Twice a day, every single day. Forever, and that's the polite version of what happens because we haven't even talked about the ground beneath your feet. Earth's tectonic plates float on a semi-molten layer, and that layer responds to gravitational stress exactly the way the oceans do. A meaningfully heavier moon doesn't just pull water, it pulls rock. Earthquakes that used to strike once in a generation start striking every few years. Volcanic regions dormant for centuries begin to stir awake. This isn't speculative fiction. This is basic tidal mechanics, scaled up to a level our planet has never had to survive in the entire history of complex life. So Kepler 10b, this scorched lava world dragged in from 560 light-years away, spends its early centuries in our sky cooling into a dark, brooding orb. While down here, we spend those same centuries reinforcing coastlines and rebuilding cities against tremors we never used to think about. And there's a second, slower danger tucked inside that cooling process. As a molten world solidifies, it doesn't do so evenly. Pockets of trapped gas and residual heat can build pressure beneath a hardening crust, the same way a sealed can builds pressure over a flame. On a planet-sized scale, that means Kepler 10b's surface wouldn't just cool quietly into stillness. It would likely keep erupting sporadically for centuries, venting trapped heat in violent, unpredictable bursts visible from Earth as sudden flares against the darkening disk, a reminder every few years that this thing hanging over our heads used to be an open wound of a planet and hasn't entirely finished healing. But we're only just getting started. Because if a slightly too heavy lava world sounds bad, wait until you hear what happens when we bring in a planet whose insides might be partly crystallized carbon. 55. Cancri A sits about 41 light-years away, orbiting so close to its star that its year lasts just 18 hours. It's roughly twice Earth's size and around 8 times its mass, and researchers have floated a theory about this world that sounds almost too strange to be real, that under crushing internal pressure, a significant portion of its interior may have compressed into diamond. Not decoration, not a headline exaggeration, an actual planet whose insides may be structured around carbon squeezed into gemstone. Now put that in the sky, where the moon used to be. 8 times the moon's mass, sitting at lunar distance, isn't a stabilizer anymore. It's a wrecking ball on a very short leash. The tidal forces we just described with Kepler 10b would look almost quaint by comparison. We're talking about tidal ranges capable of reshaping coastlines within a single human lifetime, ocean surges capable of drowning low-lying nations outright, and a level of continuous seismic stress that could render entire regions of Earth functionally uninhabitable within decades, not centuries. Here's the detail that should really unsettle you, though. Earth's rotation isn't fixed. It's being gradually slowed by the moon's gravity right now, today, adding roughly 2 milliseconds to our day every century. It's so gradual we barely notice it across a human lifetime. Swap the moon for something 8 times heavier, and that braking effect accelerates dramatically. Days that used to run 24 hours would begin stretching, minute by minute, year by year. Not in some far future geological epoch. Within a time frame where your grandchildren might genuinely notice the clocks feel wrong. And there's an even more uncomfortable possibility buried underneath all of this. A body that heavy, sitting that close, edges dangerously near what's called the Roche limit, the distance at which a planet's gravity becomes strong enough to physically tear a smaller orbiting body apart. We'd need to check exactly where 55 Cancri-E's mass places it relative to that threshold. But if it's close enough, we're no longer looking at a slow tidal disaster. We're looking at a diamond world slowly shredding into a debris ring around Earth, and pieces of that ring raining down as some of the most spectacular and most lethal meteor events in recorded history. So far, everything we've moved into the moon's orbit has been solid, rock, or something rock-adjacent. But what happens when we bring in something that isn't solid at all? GJ's and b orbits a red dwarf star roughly 48 light-years from here, and it belongs to a category of world we don't have a single true example of in our own solar system. A possible water world, sometimes nicknamed a mini-Neptune, where a thick layer of high-pressure, superheated water and steam may extend hundreds of kilometers beneath a dense, humid atmosphere. It's about 2.7 times the size of Earth, and researchers believe its atmosphere alone makes up a substantial fraction of its total volume. Move that where the moon used to be, and the sky itself transforms. You wouldn't see craters or ancient lava seas frozen into rock anymore. You'd see clouds, a permanently swirling, storm-choked atmosphere hanging in our night sky, close enough that a basic telescope could trace individual weather systems in real time. For a while, it might even be beautiful, humanity's first live view of an alien storm, glowing faintly in reflected sunlight, night after night after night. But beauty is not the same thing as safety. An object roughly 2.5 times the moon's diameter carries dramatically more mass, and more mass at lunar distance means the same tidal nightmare we've already outlined, just amplified again. And this time, there's an added complication: atmosphere interaction. A body that large, sitting that close with a dense atmosphere of its own, would begin interacting gravitationally, not just with Earth's oceans and crust, but potentially with our atmosphere too. Researchers studying extreme tidal environments have raised the possibility of atmospheric stripping in close orbit scenarios like this, meaning over sufficiently long timescales, the object could start shedding pieces of its outer atmosphere into space, some of it drifting toward Earth's own upper layers. We're not talking about a bad storm anymore. We're talking about the slow, invisible contamination of Earth's atmospheric chemistry by an alien one, molecule by molecule, decade after decade. And all the while, that same crushing tidal stress keeps doing what it's done in every scenario so far, grinding at coastlines, stressing the crust, stretching the length of our days. Except now there's a slow chemical wildcard mixed in too, an atmosphere we don't fully understand, quietly bleeding into our own. There's also a stranger possibility worth sitting with. A mini-Neptune like GJ's 1214b likely holds most of its water, not as a familiar liquid ocean, but as an exotic phase of matter, called superionic ice. Water compressed under such extreme pressure and heat that it behaves almost like a metal, conducting electricity while still technically solid. Nobody knows exactly how that material would behave once removed from the crushing pressure of its home world and subjected to Earth's comparatively gentle tidal environment instead. It might simply stay locked in its exotic state for centuries, or it might not, and if it doesn't, we'd be looking at a planet-sized phase change happening in our own backyard, releasing energy in ways no climate model on Earth has ever had to account for. At this point, you might assume the safest move would be to bring in something smaller, something less massive, something closer to Earth's own proportions. Surely that would calm things down. Let's test that assumption before we move on, because it deserves a fair shot. Proxima Centauri b is the closest known exoplanet to our solar system, just over 4 light-years away, orbiting the red dwarf Proxima Centauri. It's roughly 1.3 times Earth's mass, sitting comfortably within what astronomers call its star's habitable zone, and for years it's been treated as one of humanity's best long-shot candidates for a second home. Rocky, Earth-scale, temperate. On paper, it sounds like the safest, most boring object we could possibly drop into lunar orbit. Here's the problem. Proxima b orbits so close to its dim red dwarf star that it completes a full year in just over 11 days. And a world that close to any star is almost certainly tidally locked, meaning one hemisphere permanently faces its sun while the other sits in endless night. Pull that planet away from Proxima Centauri and drop it into orbit around Earth, and the tidal locking doesn't just disappear. Its own rotation, having spent its entire existence frozen in that locked relationship, would now have to violently readjust to Earth's much weaker but much closer gravitational grip. That's not a peaceful transition. That's a planet-wide, centuries-long process of internal stress redistribution, of a world literally relearning how to spin, with all the seismic consequences that implies. And even setting the tidal locking chaos aside, Proxima b, being roughly Earth's mass, doesn't make it a safe neighbor at lunar distance the way it might sound. Remember, the actual moon is barely more than 1% of Earth's mass, an object 1.3 times Earth's full mass. Sitting where our featherweight moon used to sit isn't a modest step up. It's roughly 80 times heavier than what's supposed to be there. At that scale, we're not discussing bigger waves or the occasional extra earthquake. We're discussing tidal forces powerful enough to physically deform Earth's crust in real time, mountains rising and falling as the two worlds pull at each other every single orbit, an entire planet flexing like a stress ball twice a day. So even the candidate that looked on paper like the calm, familiar, Earth-like option turns out to be one of the most violently destructive choices on this entire list. Turns out Earth-like and safe at lunar distance are two very different things. It wouldn't, because we haven't shown you the worst one yet. WASP 12b sits about 4,400 light-years away, and it holds one of the grimmest distinctions of any confirmed exoplanet. It is actively being devoured by its own star, orbiting once every 26 hours, so close that its host star's gravity has stretched it into an egg shape. It's continuously losing its outer atmosphere in a stream that forms a glowing disk of stolen gas swirling around the star itself. WASP 12b is roughly 1.4 times the size of Jupiter. Jupiter? Not Earth, not the moon. Jupiter. We are talking about dragging a gas giant, one already being torn apart by extreme gravity in its home system, into lunar orbit around Earth. Let's be completely clear about the scale here, because it breaks the pattern of everything we've discussed so far. The moon has a mass of roughly 7.3 x 10^22 kilograms. A Jupiter-class planet like WASP 12b would carry a mass in the range of 10 toward 27 kilograms, tens of thousands of times heavier than the moon we're used to. At lunar distance, that isn't a tidal disturbance. That's an extinction-level event compressed into weeks. The Roche limit exists for a reason, and there is no version of physics where a Jupiter-mass world survives intact at 384,000 kilometers from Earth. It would begin fragmenting almost immediately, shedding gas and debris in a spiraling, catastrophic collapse. Earth's oceans, already stressed to breaking point by everything we've walked through, would be thrown into tidal bulges dozens of meters high, not centimeters. Coastal civilization wouldn't have decades to adapt to this one. It would have days, maybe less. And that's before we even consider what happens to Earth's own orbit. A gravitational anchor, tens of thousands of times more massive than the Moon, sitting at lunar distance, doesn't just tug at tides. It begins to drag at Earth's path around the Sun itself. Our rotation, our seasons, our entire climate stability depend on a delicate balance that took billions of years to settle. WASP 12b in the Moon's orbit doesn't disturb that balance. It shatters it and takes us down with it. And here's the timeline that should really unsettle you. This isn't a slow-motion catastrophe stretched across generations, the way the tidal disasters we described earlier were. Orbital decay for an object this deep inside its Roche limit happens on the scale of days to weeks, not decades. The first visible sign might just be a faint haze forming around the planet's edge, gas beginning to stream away into space. Within days, that haze would become a visible tail, glowing faintly as it caught the sunlight, arcing across the night sky like something out of a disaster film. By the time governments finished convening, emergency sessions to discuss it, the debris would already be raining down and the tidal bulges would already be swallowing coastlines that had never seen anything like it in recorded history. There's no evacuation plan built fast enough for that kind of collapse. There's no adaptation strategy, no coastal engineering project, no early warning system currently in existence anywhere on Earth that could realistically get ahead of a Jupiter-class planet disintegrating at lunar distance. Every other scenario in this experiment, however severe, at least offered decades or centuries to prepare. This one doesn't. This one just happens. So if a Jupiter-class world at lunar distance is unsurvivable, what could possibly be worse? There's one more candidate, and it isn't even light-emitting in the way you'd expect. TRES-2b, discovered around 750 light-years away, holds the title of one of the darkest known exoplanets, a world that reflects less than 1% of the light that hits it, absorbing almost everything. It's roughly Jupiter-sized as well, and its surface, if you can call the top, of a gas giant's atmosphere a surface, sits at temperatures over 1,000 degrees Celsius, glowing a faint, dull red from its own residual heat, rather than from reflected starlight. Move that where the Moon used to be, and something strange happens to our nights. Instead of a bright, reflective disk lighting up the dark hours the way the Moon always has, we'd be left staring at something closer to a black hole in the sky, a dim, barely visible shape you could only make out by the faint red glow bleeding off its own heat, and the stars it blots out behind it. Our nights, for the first time in human history, would get darker instead of brighter. But don't mistake darkness for safety. TRES-2b carries the same catastrophic Jupiter-class mass problem as WASP 12b, the same tidal bulges, the same Roche limit violation, the same slow-motion gravitational shredding, just wrapped in a black, heat-radiating shell instead of a reflective one. If anything, it might be worse psychologically, watching a dark, smoldering shape slowly disintegrate above you, with almost no visible warning. No bright flare to signal how close the collapse has come until the debris is already falling. Here's the pattern, if you've been paying attention. Every single object we've tried to place in the Moon's orbit fails for a different reason. Too hot, and we buy ourselves time while it cools, but we pay for that time in earthquakes. Too heavy, and the tides alone reshape civilization within a lifetime. Too gaseous, and we risk a slow atmospheric contamination we may never be able to undo. Too massive on the Jupiter scale, and we're not looking at disaster anymore. We're looking at extinction, measured in weeks instead of centuries. There's one more candidate worth pausing on before we get to our final scenario, because it doesn't fail the way any of the others did. It fails in a way that's almost invisible. PSR B1257 plus 2 is a pulsar, the rapidly spinning, collapsed core of a star that already died in a supernova explosion, roughly 2,300 light-years away. Somehow, against every expectation, it hosts a small family of planets, worlds that most researchers believe condensed out of the wreckage left behind after that supernova detonated. These aren't gas giants, and they aren't lava worlds either. They're modest, rocky bodies, a few times the mass of Earth at most, quietly orbiting the corpse of what used to be a star. Move one of them into lunar orbit, and at first glance, this might genuinely be the gentlest option we've tested. No molten hemisphere, no diamond interior threatening to shred into a debris ring, no Jupiter-class mass violating the Roche limit within days. Just a modestly sized rocky world, broadly Earth-like in scale, settling quietly into the sky where the Moon used to be. But a planet born out of a supernova's wreckage carries the fingerprint of that violence baked directly into its composition. Elevated concentrations of heavy radioactive isotopes forged in the extreme heat, and pressure of a dying star. Instead of a tidal catastrophe playing out over decades, we'd be facing something almost impossible to notice at first. A faint, persistent increase in background radiation washing over Earth's night side every single night for as long as that world remained in orbit. Nothing dramatic, nothing that shows up on the evening news in year one. Just a slow generational creep, elevated cancer rates, subtle genetic stress on wildlife populations already straining under everything else, accumulating quietly for as long as nobody thinks to look up and ask why. It's a reminder that the most dangerous replacement for the moon isn't necessarily the one that looks the most violent from a distance. Sometimes it's the one that looks the calmest. But there's one scenario left we haven't tried, and it might be the strangest of them all because it isn't a planet in the traditional sense at all. Somewhere out past Neptune, drifting through interstellar space with no star to call home, there are worlds astronomers call rogue planets. Planets that formed around a star and were later flung out entirely, or that never had a star to begin with. We've detected several candidates through gravitational microlensing, the same shadow and light technique that revealed Ogle, 2005 BLG 390LB earlier in our experiments, and some of these rogue worlds are estimated to be Earth-sized, or close to it, wandering the galaxy in permanent absolute darkness. Pull one of those into the moon's orbit, and on the surface, it might look like the gentlest option we've discussed all day. A modestly sized rocky world, roughly Earth's scale, no lava ocean, no diamond core, no Jupiter-class devastation waiting to unfold. But that surface calm hides something else entirely. Something that has nothing to do with mass or tides. A planet that spent unknown eons drifting alone through interstellar space with no star to warm it would arrive at Earth as an object cooled to nearly absolute zero, hundreds of degrees below anything in our solar system's own experience. Dropped into lunar orbit, it wouldn't threaten us with fire or flood at first. It would threaten us with cold, a permanent deep space chill radiating outward from an object sitting just 384,000 kilometers away, subtly pulling down the temperature of everything nearby, night after night, for as long as it took to slowly, painfully warm. It's the quietest of every scenario we've explored today, and maybe that's exactly what makes it the most unsettling. No spectacular tidal collapse, no visible storms, no cracking crust, no apocalyptic countdown, just a dark frozen shape hanging in our sky and a slow, patient chill settling over everything beneath it, while everyone insists nothing seems that different, right up until it very much is. Now step back and look at everything we've just done. 8 worlds, 8 star systems, 8 completely different origin stories, all funneled one after another into the same 384,000 kilometer orbit that our actual moon has occupied, quietly and without complaint for over 4 billion years. Not one of them worked. Not one of them was survivable long-term, and several of them weren't survivable at all. Line them up, and the failures start to form a pattern that feels almost designed to teach a lesson. Kepler 10b showed us that even a world that eventually cools down can still wreck us on the way there, through gravity alone. 55. Cancri showed us that mass, more than heat, is the real threat hiding in plain sight. GJ 1214b showed us that even something as harmless looking as weather can hide a slow chemical contamination we might never fully reverse. Proxima b showed us that Earth-like is a meaningless comfort once you change the distance and the mass ratio involved. WASP 12b and TRES 2b showed us what true unsurvivable overkill looks like, extinction measured in weeks rather than centuries. The Pulsar world showed us that the quietest, calmest looking option can still be lethal, just on a timescale too slow for any one generation to notice until it's far too late. And the rogue planet showed us that even removing all the fire and all the mass and all the radiation still leaves something capable of quietly freezing this planet from 384,000 kilometers away. There is no version of this experiment where the outcome is neutral. The moon isn't just a light in the sky we've grown sentimentally attached to. It's precisely calibrated by 4.5 billion years of gravitational accident to be exactly massive enough to stabilize this planet and exactly far enough away to do it gently. Every alternative we explored today either did too little, too late, or far, far too much, too fast. And think about what that actually means for the scale of the coincidence we're living inside of. We didn't design the moon. Nobody engineered its mass to sit at 1% of Earth's, or its distance to land at exactly the point where its gravitational pull calms our oceans instead of drowning them. It's the leftover debris of a single violent collision 4.5 billion years ago that happened to cool into precisely the right shape, at precisely the right distance, move that impact by a slightly different angle, at a slightly different speed, and the moon we got could just as easily have been too close, too heavy, too erratic, and none of us would be here to notice the difference because there wouldn't be an us to notice anything at all. That's the part this entire experiment keeps circling back to. Whether we're talking about a lava world, a diamond planet, a storm-choked mini-Neptune, or the quiet radioactive glow of a Pulsar's child. Every single one of them is a planet that somewhere else in the galaxy might be perfectly fine, might even be somebody else's version of a stable, livable world. The problem was never really the planets themselves. The problem was proximity. The problem was forcing worlds shaped by entirely different histories, entirely different stars, entirely different gravitational arrangements into an orbit that was custom built by pure accident for one very specific object and nothing else. And that raises a question none of these scenarios really answer. If nearly every rocky, icy, or gaseous world we know how to find turns lethal the moment we bring it close, enough to replace our moon, what does that tell us about how rare our current arrangement actually is? How many other planets out there once had a moon like ours, stable, steady, quietly protective, before something disturbed it? A near collision, a passing rogue world, a slow gravitational drift over billions of years. How many of them lost their tidal anchor the hard way and never got the chance to build anything like what we've built here? We don't know. Nobody does. But somewhere out there, among the thousands of exoplanetary systems we've already cataloged, there could be a world going through exactly this transformation right now, in real time. Its own moon slipping away or being replaced, not by some curious experiment like ours, but by the ordinary indifferent chaos of a galaxy that never promised anyone stability in the first place. Maybe it's happening to a red dwarf system we've barely begun to study, some rocky world losing its tidal anchor to a near miss with a rogue planet drifting through, its oceans just beginning the same slow transformation we walked through today, its own version of a civilization, if one exists there at all, having no idea their sky is about to change forever, or maybe it already happened millions of years ago to a world that used to look a lot like ours. And all that's left now is a barren, tidally battered ruin orbiting a star that never noticed the difference. We like to think of the moon as permanent, as background scenery, as the one constant in a universe defined by chaos and collision. But every experiment we ran today says otherwise. It says the moon is a coincidence, a fragile, precisely balanced accident that happens to still be working, for now. And if that's true, then the real question isn't what would happen if we swapped our moon for something else. It's how much longer the one we already have is actually going to stay right where it is.